Good morning to all of my students. Myself, Mr. Dibyendu Mondal, Assistant Professor of Mechanical Engineering Department of Greater Kolkata College of Engineering and Management under JIS Group. In this pandemic situation, I am delivering my lecture through online mode and my video is uploaded in YouTube.
Good morning. I am Mr. Dibyendu Mondal. Today I am taking a class of air compressor. Actually, air compressor are used for supplying high pressure air. There are many uses of high pressure air in the industry. The main uses of high pressure air are: first one, to drive compressed air engine used in coal mines, to inject or spray fuel into the cylinder of a diesel engine, air injection diesel engine, to operate drills, hammers, air brake for locomotives and railway carriages, water pump and paint sprays, to start large or heavy diesel engine, to clean workshop, machine, generator, automobile, vehicles, etc. To operate blast furnaces, gas turbine plants and Bessemer converters used in steel plant. To cool large building and aircrafts. To supercharge IC engine. There are mainly two types of air compressor, that is reciprocating air compressor and rotary air compressor. Reciprocating air compressor are similar Reciprocating air compressor are similar to reciprocating engine, where a piston reciprocates inside the cylinder. In rotary air compressor, air is compressed due to rotation of impeller and blades inside a casing. Air compressor are driven by the engines or electric motor. In this chapter, the theory of reciprocating air compressor is discussed in detail, and principle of working reciprocating compressed air motors and rotary compressor are explained in brief. Now, reciprocating air compressor. Reciprocating air compressor, actually the principal parts of reciprocating air compressor are the same as that for the engine. The reciprocating air compressor may be single acting. Air is admitted to one side of the piston only, or double acting, air is admitted to each side of the piston alternatively, and may be single stage or multi stage. In a multi stage compressor, the air is compressed in several stages instead of compressing the air fully in a single cylinder. This is equivalent to number of compressed arranged in series. The pressure of air is increased in each stage compressor for pressure up to 200 bar, and two-stage compressor for pressure in between 10 to 200 bar. The average piston speed of a reciprocating air compressor is limited to about 300 to 400 meter per minute to reduce friction wear. First one, the single stage air compressor. Actually, the sectional view of an air-cooled single-stage, single-acting reciprocating air compressor, both intake and discharge valves are the disc type and are automatic in their action. They are opened and closed by difference in the air pressure acting on their two sides. When the pressure are equal on their two sides, they are kept closed by the light spring. During the outward or suction stroke, the pressure in the cylinder falls below the atmospheric pressure, as a result of which the intake valve opens and air is drawn from atmosphere into the cylinder. During the inward or compression stroke, as a result of the piston action, the pressure of the air in the cylinder gradually increases and reaches a value sufficiently above the receiver pressure. The high pressure of air thus produced overcome the resistance of the spring on the discharge valve and causes the valve to open and discharge takes place from the cylinder to the receiver. The receiver is a simple vessel which acts as a storage tank. The compressor is driven by some form of prime mover. Okay, prime mover. And this is the diagram of sectional view of a single acting air cooled reciprocating air compressor. Okay, now indicator diagram. Indicator diagram actually, the event described above can be conveniently represented by the PV diagram shown in the figure. The diagram is drawn for a compressor without clearance. During the suction stroke, the discharge of air, the charge of air is drawn into the cylinder along the 4-1 at constant pressure P1, which is slightly below that of the atmosphere. At point 1, the piston completes the suction stroke and starts on its return stroke. All the valves are being closed the air compressor. Okay. At point 2, pressure P2 is reached, which is slightly higher than the pressure in the receiver. The discharge valve at this point opens and the delivery of the compressed air takes place along the line 2-3 at a pressure P2. The piston has now reached the left hand end of the cylinder and again starts on its suction stroke, and the pressure in the cylinder will be lowered again. The net work required for compression and delivery of the air per cycle is represented by the area 1, 2, 3, 4. Okay, so this is the diagram 1, 2, 3, 4. Compression curve, delivery, another one is the suction. So this is the pressure volume diagram. The piston has now reached the left hand and the cylinder and again starts on its suction stroke, and the pressure in the cylinder will be lowered again to P1 and the cycle operation will be repeated. The net work required for compression and delivery of the air per cycle represented by the area 1, 2, 3, 4. The amount of work done on the air will depend upon the nature of the compression curve. If the compression occurs very rapidly, in a non-conducting cylinder so that there is no heat transfer. The compression will be practically isentropic. If it is carried out slowly so that heat of the compression is extracted from the air by the jacket cooling water. The compression will approach the isothermal. However, in actual practices, neither this condition can be fulfilled and the actual compression line be between isentropic and isothermal. Isothermal compression versus isentropic compression. Actually, the slope of the compression curve represented by the law Pv to the power n is equal to constant depends upon the value of the index n. A large value of n will give comparatively a steeper curve. The law for isothermal the law for an isothermal or hyperbolic compression is Pv is equal to constant, where the value of index n is unity. The law for an isentropic compression is Pv to the power gamma is equal to constant. Since the value of gamma for air is 1.4, the isentropic curve will be steeper than isothermal curve. The figure shows the curve representing an isentropic compression and an isothermal compression. The isentropic work required to be done per cycle on the air is represented by the area 4, 1, 2, 3, 2 prime 3. If the compression carried out have been isothermal, the slope of the compression curve would be less than that of isentropic, and the isothermal work done would be represented by the area 4, 1, 2 prime, 2 double prime 3, which is evidently less than the isentropic work done represented by the area. Therefore, it follows that an isothermal compression is economical and efficient, since less work is required to carry it out, while an isentropic compression requires more amount of work to be supplied. Compression curve with values of index n between 1 to 1.4 will fall within the isothermal and isentropic curve. Thus, it will be seen that the work required for compression and delivery of air per cycle decreases as the value of n decreases. The theoretical indicator diagram for a single stage compressor without clearance is shown here. Here, the air actually V1 meter cube, P1 Newton per meter square or Pascal, and the final delivery pressure after compression, then work required to be done on the air W per cycle, assuming compression curve to be polytropic. Pv to the power n is equal to constant is given by the area 1, 2, 3, 4. Now area 1, 2, 3, 4 and area 0A, 2, 3 plus area 2, 1B, this area minus B140. P2 V2, actually work done in polytropic process, P2 V2 minus P1 V1 divided by n minus 1 minus P1 V1. So you may write down n P2 V2 minus P2 V2 plus P2 V2 minus P1 V1 minus n P1 V1 plus P1 V1 n minus 1. So W is equal to n by n minus 1 P2 V2 minus P1 V1 joule per cycle. So W is equal to n by n minus 1 AMR T2 minus T1 joule per cycle. Taking P1 V1 outside the bracket, W is equal to n by n minus 1 P1 V1 P2 V2 by P1 V1 minus 1. But for polytropic compression, P1 V1 to the power n is equal to P2 V2 to the power n. Hence, V2 by V1 equal to P2 by P1 whole to the power minus 1 by n. Substituting the value V2 by V1 in the above equation, work required per cycle per revolution if compressor is single acting. So W is equal to n by n minus 1 P1 V1 P2 by P1 into P2 by P1 whole to the power minus 1 by n minus 1. So n by n minus 1 P1 V1 P2 by P1 whole to the power n minus 1 by n minus 1 joule per cycle. This equation gives the work required in joule per cycle per revolution if the compressor is single acting in compressing and delivering the air. It should be noted that units of compressor and volume in equation this indicated power of the compressor W into n by 60 joule per second. W is equal to work required in joule per cycle. N is equal to number of cycle performed per minute equal to RPM for single acting compressor if P1 V1 in equation is substituted by MRT1. Then the work required per cycle W equal to n by n minus 1 MRT1 P2 by P1 whole to the power n minus 1 by n minus 1 joule per cycle. Work required per kg of air W equal to n by n minus 1 RT1 P2 by P1 whole to the power n minus 1 by n minus 1. So you may write down indicated power of the compressor W into mass of air delivered per second, that is equal to joule per second. If the compressor is an isentropic process, so that is the PV to the power gamma is equal to constant. The index n will be replaced by gamma in this equation. Work done W is equal to gamma by gamma minus 1 P1 V1 P2 by P1 whole to the power gamma minus 1 by gamma minus 1 joule per cycle. So work required per kg of air W is equal to gamma by gamma minus 1 RT1 P2 by P1 whole to the power gamma minus 1 by gamma minus 1 joule. If the compression is isothermal, PV is equal to constant, then work required per cycle W is equal to area 1, 2, 3, 4. So area is equal to area A21B plus area 0A23 minus area B140. So W is equal to P1 V1 log E V1 by V2 plus P2 V2 minus P1 V1. So the final expression P1 V1 log E P2 by P1 joule per cycle. Therefore, work required per kg of air at T1 log E P2 by P1 joule. That is the work required per kg of air. Okay.
Last, if you like my video, you have to subscribe. Okay, thank you.